Good day, learners. Welcome to Technical Sciences lesson. My name is Zamisile Mdima. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Okay, so today we are going to be looking at terms 2 content in grade 11, and first up we're going to be focusing on magnetism. Okay, so let's get started by getting an overview on what we're going to be looking at on magnetism. So first up, we need to know magnets, being able to define them, how they look like. We need to be able to define a magnetic field. We need to be able to know how to use a compass in magnets, okay, so that we find the direction. And we need to be able to predict the behavior of magnets when they are brought closer to each other, how they're going to interact, what force they exert on each other without being physically touched. We're going to be looking at properties of magnetic fields so that we are able to draw the magnetic field lines correctly. And lastly, we're going to be focusing on the magnetic field strength. When is it weak and when is it stronger? And what are those things that affect the magnetic field strength? Okay. Our objectives are what we should know by the end of today's lesson. We should be able to define a magnet. We should be able to define a magnetic field. We should be able to use the compass to determine the direction of the magnetic field. Also, by the end of this lesson, I want you and I to be able to sketch the magnetic field of the bar magnet. Also, to be able to predict the behavior of magnet when they are brought closer together. And lastly, to be able to understand and implement properties of magnetic field lines. All right. So I know you and I are going to be just great once we are done with this lesson. We're going to be able to define and determine all the things on our objectives. Okay. So let's get started. What is magnetism? Okay, you may ask yourself, magnetism is an interaction that allows certain kinds of objects, which are called magnetic objects, to exert forces on each other without those objects being physically touching. So what we mean is that a magnetic object is therefore surrounded by what we call a magnetic field that gets weaker as you move further away from the magnetic object. Okay, so a second object can feel more magnetic force from the first object because it feels more of the magnetic field of the first object, but the further away, the weaker the magnetic force the object will experience. Okay, but then it raises a question: what is then a magnetic field? A magnetic field is a region in space where a magnet or an object that is made of a magnetic material, we experience a non-contact magnetic force. Now, we cannot see this magnetic field, but we can see their effects. So hence, it is important for us to know how they are drawn so that we can best understand their effects. Now, we've got materials that we call ferromagnetic material. So in simple terms, it's just a substance that shows spontaneous magnetization. Okay, that simply means that that material has a magnetic field around it without any external forces being required. Okay, so it's spontaneous means that it is self-generated or happens without any external force. All right, now such materials are made of cobalt, that are made of nickel, that are made of iron as well. Now you can include even the iron ores on that one. Now, why is it all like that? It's because the domains in the permanent magnet, what they do is that they line up in a particular direction. The magnet then or rather has poles that are then called the north, which is abbreviated by a capital letter N when you see it in a magnet, or abbreviated as a capital letter S, which is shortened for south. So in a typical magnet, this is what you will see. You pretty much have your south pole and then you've got your north pole. Now, if we take this magnet and we crush it into tiny, tiny, tiny pieces, what you will see is that all these tiny pieces of the magnet will each and every piece in there will have a south pole and will also have what? A north pole. Now, that is why we even included that even if the magnet is cut into tiny pieces, each piece will still have both poles, which is your north pole as well as your what? As well as your south pole. Now, these magnetic poles, they always occur in pairs in nature. Then we never find a north pole just roaming around on its own or a south pole roaming around on its own. So they always go in pairs. Then the magnetic field can be represented using the magnetic field lines. Remember, we had said the magnetic field is a region in space where a magnetic material or a ferromagnetic material will experience a non-contact force, which we call a magnetic force. Now, because it is invisible, we try to represent this magnetic field using the arrows and the lines so that we can best indicate the direction on which we talk about the force of attraction, or rather the force of repulsion, depending on the poles that are brought closer to each other or the poles that are interacting. Okay, now the magnetic fields can be represented using the magnetic field lines starting from the North Pole and ending at the South Pole, and that is always the case. Your magnetic field lines will move from the north and goes to the South Pole. And if you're talking in terms of a bar magnet, like the one we just portrayed for you, that means that those magnetic field lines are continuous. So what we portray on the outside does not mean they're always going to be moving from north to south and then they end there. No, even from the south, they move from the south to the north, but within the magnet. But only what we write for the magnetic field is what we is on the outside, the interaction that is on the outside. But bear in mind that magnetic field lines are continuous, just that when we are drawing the lines, we are drawing them from the outer part of the magnet, from the north, and they are being received on the south pole of the magnet. But it does not mean they end there. They also go through the magnet from the south to the north within the magnet, and then right on the outside again from the north into the south. That is why we say they are continuous like that. Okay, now the number of the field lines drawn crossing a given dimensional surface is therefore referred to as the term that we give it. It is magnetic flux. So if we have the magnetic flux is then used to measure the strength of the magnetic field through that particular surface. Okay, so that means the magnetic flux has got a direct relationship with the magnetic field strength. So remember, or rather, if there we have more field lines that are drawn, that means we have a higher strength of the magnetic field. Okay, so that is why we say there is a direct proportional relationship between the magnetic flux and the magnetic field strength. Okay, so that is why we included in there that the closer together the field lines, the greater the field strength. Okay. Also, what is very, very important is that these magnetic field lines, they never cross and they never touch. Okay, so that is something that we need to pay attention to when we are drawing the magnetic field lines. Okay, so without wasting any time, let's look at the variety of the shapes of or the types of the magnet that we can find out there. Now, the magnets come in a variety of shapes. Okay, the one that is common is that of a horseshoe. Horseshoe has got a U-shaped kind of magnet. Okay, now the horseshoe magnet has the north and the south pole. Remember, we had said these poles are always going in pairs. You'll never find the south pole just roaming around on its own, even when these or rather the magnets are crushed into tinier pieces. All right, so the horseshoe magnet has north and south pole just like a bar magnet, but the magnet is just curved so that the poles, they lie in the same plane, as in the diagram that is shown for you. Now, the magnetic field lines, they flow from pole to pole, remember, and the sequence, or rather the direction of the movement of these field lines is that on the outer part, it's moving from the North Pole to the South Pole. South Pole is receiving, that is externally, but then moves continuously, move from the south to the north in the inside of the magnet. But in this case, we're talking about the horseshoe, which is a U-shaped magnet. Okay. So however the poles are located closer together, or the direct path is then exists so that the traveling between these poles are more concentrated at the poles. So you can see in the diagram that is provided for you, you've got your the magnetic field line from the north to the south, and then continuously inside the horseshoe U-shaped magnet, and then on the outside again. Then, what happens then when two bar magnets are brought closer to each other? Okay, now it depends on the type of poles that are interacting at that particular time. Now, when two bar magnets are brought close together, their magnetic fields interact. All right, so we sum it up nicely by saying, unlike poles, when something is unlike, it's your north as well as your south that is being brought together. So what you find is that their magnetic field, they then interact and cause the two poles to attract one another. But if we bring the like poles, okay, like means the same, like we're bringing the north as well as the other north, what you'll find is that their magnetic field interact and they repel away from each other. Okay, so this magnet will then push the other magnet on the other side. They will not attract each other because they are of the same. So it's north and north, and then it's south of the south. Now in the diagram provided to you, you can see that at the top there, you've got your north and your south, and they are attracting. But if we had to draw showing their magnetic field lines, then we'll show that these are moving from the north, moving nicely to the south, and vice versa, and continuing inside the magnets as well. But if you look at the diagram below, you'll see that because they are like poles, they are the same. So in this instance, they've shown you north and north, therefore they are repelling. Their magnetic field are not touching at all, and instead they are just pushing each other on the opposite ends. But then, what are the things that we should be cautious about when we are drawing these magnetic field lines? What are the things that we should pay more attention to? Okay, so there are pretty much properties of the magnetic field lines that have a number of the things that we have to look at. Okay, first one is that they seek the path of least resistance, because now between the opposite poles in the single bar magnet, as shown in the right of the diagram that I just shown you, they attempt to form closed loops because they're always trying to look for the path of the least resistance, where they can just move easily from one pole to another. Okay, the second one, they never cross one another. All right, they should never cross one another. They all have the same strength. Okay, their density decreases as they spread out. Right, so you'll find that they will be more concentrated at the poles, but as they spread out in the middle of the magnet, then they start being less and less and less. That means that their magnetic flux then decreases, because now the number of magnetic field lines therefore does what? Decreases. Okay, when they move out of that area of the higher permeability to an area of what? Of low permeability. Okay, an area of high permeability being that of in the poles, and then going in the middle of your magnet. Now their density decreases with an increase in the distance. All right, so as you move them far away from each other, they start now to experience less force than they would experience when they are brought closer to each other. Okay, now they are considered to have a direction as flowing through, though there is no actual movement that is occurring. Remember, we had said that they just continuous lines like that. There is no actual movement that is flowing, but they are considered to have a direction as if they are flowing. Okay, they flow from the South Pole to the North Pole within the material, but on the externally part of the magnet, they move from the North Pole to the South Pole in the air. Now, not only are there types of different magnets, like your horseshoe, U-shaped magnet, like your bar magnet. Also, the Earth itself is considered to be magnetic. Why is that? Or why does it have its own magnetic field? Okay, let's explore that part. Now, the magnetic field of the Earth emanates with the fact that from the liquid iron core of the Earth. Okay, now because the iron core is molten, when something is molten, is liquid-like, and therefore it is in constant motion. It's not stagnant, it's not stationary, it is in constant motion. Now, since the iron is a magnetic material, also it is no surprise that other smaller magnets on the Earth will then be affected by what? By the iron, the molten iron core of this Earth. Now, the constant motion of the molten iron ore then causes a variation in the Earth's poles. So now you find, instead of having just one pole, you're going to have like two poles in the Earth. We're going to have, so actually the Earth poles are now moving, because now the poles of the Earth are now moving due to the molten iron core of the Earth. Now, the actual North Pole of the Earth and the magnetic north of the Earth, therefore, do not coincide, meaning they are not in one direction. They differ by a certain angle of declination. Now, they're not in the same position, if we can put it in simple language. This is obviously because of the moving molten iron core. All right. Now, the difference between the geographic north, the one that we can pinpoint geographically using our maps, we call that one to be true north. And the other one, north, that is due to a motion one due to the iron core, we call that one a magnetic North Pole. So now the Earth, at the end of the day, therefore gets to have a geographic North Pole due to direction that we'll use in compass direction, your north, your south, your west, as well as your what? Your east. Okay? And then we have a magnetic pole, which is then due to the fact that there is a molten iron core which is magnetic, making it to differ in position from the true north, the one that we call a geographic north, or rather the true north. Okay, that difference between the true north and the magnetic north pole, we call it an angle of declination, and it's usually a difference of about 11.5 degrees. So there's a distance between those two poles, and the distance get increasing because the one that is a magnetic north is therefore moving towards the center of the Earth, which is your equator. So what does all this mean? This means that the magnetic north is heading towards the equator, okay, by 11.5 degrees. Suddenly, a flip will take place, and what was north then becomes what was south, and what was south will then now become what was north. Okay, so that is how the Earth's magnetic field then affects, okay, the geographic north, and then as well as the magnetic north. All right. So let's put this now into practice. Let's talk in terms of the questions that they may ask you when they are assessing you in terms of these this topic, which is magnetism. In the question in here, it is a multiple choice question. Don't forget that with your multiple choice question, there is always 4 options that are presented to you. So 2 of them are your distractors and 2 are the most correct ones. So for you to be able to choose the most correct answer amongst the 4 that is provided to you, you should be able to just see the ones that are distracting you from finding the correct answer, and then you deal with the 2 and identify a correct answer. Okay, so the question that is presented to us right now is saying a bar magnet is cut in half and divided into pieces. Which one of the following statements is true regarding the force between A and B if they face each other with a small separation between them? And they gave us a good diagrammatic representation here. So this was a full magnet with a north as well as south pole, but it's not indicated in that magnet. Okay, so the other half is a south, the other half is a north, and then record it in the center. So remember what we had said is that even when we cut the magnet into tinier pieces, each piece will have a north and will also have what? The south. Okay, assuming either or, you had your north on the other side and your north on the other side. So even if you cut them into 2, piece A is still going to have a north pole and a south pole. Piece B is still going to have a north pole as well as what? As the south pole. Okay, so now if you had a south on this side and on this side, if you had a north on this side and had a south on that side, that means if you cut them in the middle, the one with the south would then have what? Its north, and the one that had its north will therefore have it what? Its south. So let's look at the options that they've given us. They're saying A, there is a magnetic repulsive force between A and B. B, second option, there is a magnetic attractive force between A and B. C, there is a magnetic attractive force between A and B. Then they start to repel each other when they come into contact. Or D, which is the last one, there is no force between A and B. Okay, so rest assured, over here, you had your north and then you had your south. Now, when it is cut into tinier pieces, this then will be your north and this will be your south, because now each and every piece will have that. So these are unlike poles and therefore will do what? Will attract. Number 2, they are saying draw the magnetic field lines around the following magnets. So what they've done is that they've given you different types of magnets, and they want us to implement the properties of the magnetic field lines. Okay, so you've got a north over there at the top, and then you've got a south. So remember, externally, this, because we draw the magnetic field lines externally, we had said they move, the magnetic field lines will move from the north to the south. So you should be able, even if you draw a few of them, so that you make sure that they never cross each other, because this is an important property of the magnetic field lines. So I'm going to draw just 2, and then on this direction as well. And on either side, I do 1. Okay, they should never touch. Okay. Right. Okay, so now it's time, because we've made sure that they are not touching, they are not crossing, and then we pay attention to the direction. So put that using a different pen, from north to the south. Okay, from the north to the south. All right, they have to be going down because they are moving from the north to the south. And on the South Pole, they are getting in. And from the North Pole, they are moving away from the North Pole. So that's how you then will draw your magnetic field around this specific bar magnet. Okay, this one is a bar magnet, and we have your U-shaped, your horseshoe, and this one steel. Okay, let's draw 2 on this one. Remember, less is more, so that you don't end up making mistakes when then you are drawing it. So it's from your north to the south, from your north to the south. Okay, so we indicate this magnetic field using arrows to indicate their direction. Okay, remember we had said that they are not visible, but we can draw their effects, and we know that they're always moving from north to south, and within the magnet itself, they therefore move from the south to north, hence they are continuous like that. So moving in that direction within the bar magnet, okay, or rather the U-shaped horseshoe magnet. Now, number 2 is saying the following sketch represents 2 different cases where the permanent magnets interact to each other. Now, each case, draw the field lines between the 2 magnets. All right. So between the 2 magnets that are poles, or rather 2 pieces of magnet that are put in there, on the first one or the top one, you've got like poles, and like poles means that they are going to repel. Whether it was a north to north, in this case they've given us a south to south pole. So what is happening is that because they are pushing, the magnetic field lines are pushing each piece of magnet on the opposite poles, so it's going to be represented like this. So this is a force of repulsion that is happening. So both of them are getting in. Okay? Because remember, the magnetic field lines are moving from north to south. So on the South Pole, they are getting in, or they are moving inwards. Okay? In cases whereby these were north to north, also you need to pay attention to the direction. But in that case, this is how it would look like. So you will have your north, and then you'll have your north on the other side. So it's still a force of repulsion. However, the direction of the arrows then changes, because now you've got a north to north. Right? So they are moving away, okay, from north, because they're always moving from north to what? To south. So your arrows will be showing an outward movement, not an inward movement. Okay, so that's how it would look like. Trying for them not to touch as well, because that is important. So they're most focused on the poles, and then as you move in the center of the magnet, then the strength, or the magnetic field strength, therefore decreases, but it is more concentrated on the poles of the magnet. Okay, so the second one is therefore unlike poles, and in this case they are attracting. Okay, so that means that the magnetic field lines are causing that force of attraction between the two magnets. Okay, let's use a different pen so that you can see this one. So there is movement from the north to the south. Okay, and then on this side, let's have one going up, and let's have one going down, one going up, and let's have one going up, like that. Okay, this one I don't want it to touch. Okay, okay, now in between the two poles, now there is movement of the field lines. So the field lines, the direction of the magnetic field lines is therefore from north to south, like that. And then on the south part, therefore they are getting in, or they're moving inward, they're showing the inward direction. Inward direction. But on the other side, which is then your, remember this is your south, that will means that this is your north, and this is your north, that means this is your south in here. So don't forget that on this side, let's correct this one. They're moving away. Okay, even on the other side, this side they are getting in. Let's just make one so that it's nice and tidy. Okay, to south from the north. That, there you go. Even on this side, so that it's easier for you to see, let's just make it 1 1. Okay, so it's from the north to the south, and the one that are interacting with each other from the north as well to the south. Okay, so here's this activity that I want you to try out pertaining the magnetic field, being able for you to being able to now draw the magnetic field lines according to the way it should be by following the properties of the magnetic field lines. Okay, so I'm just going to highlight it for you and then give you clues on how to go on about it. So it's question 8 is taken from one of the previous papers in 2023. Now 8.1 is saying a bar magnet has a pair of opposite poles called the north as well as the south. Okay, now the figure below shows a bar magnet with its poles. So you've got your north and as well as you've got your south, and it's just a typical magnet that is presented to you. So 8.1.1, define the term the magnetic field. Okay, a magnetic field, remember you have to define it the way it is a region in space where a magnetic or a ferromagnetic material will experience a force. Okay, so 8.1.2, draw now a magnetic field pattern around the bar magnet. Okay, what you need to remember is that the magnetic field lines, they never cross, and also they never cross each other. they always run from north to south pole on the outside, and then the magnetic field strength is more concentrated on the poles. They are continuous, and you continue with all those ones. But now you are implementing all these properties in drawing, in drawing them up. Okay. But it's one bar that is given to you, so you need to move from the north on the outside to the south. You don't necessarily need to draw the magnetic lines inside the magnet. We just focus on the magnetic field lines on the outside. Okay. 8.2 is saying the north pole of the bar magnet is brought closer to south pole of another bar magnet. Okay, so you've got your north south, and then you got north south on the other side. So that means that the unlike poles are facing each other. Okay, so what is it that's going to happen? 8.2.1 is the question that is asking a diagram pertaining the magnets that are presented to us right at the top. Now, is the force experienced by the magnets when they are brought closer an attraction or repulsion? You look at the poles that are facing each other or that are interacting with each other, whether they are like poles or they are unlike poles. If they are unlike poles, like in this case, because it's south and north, therefore there will be a force of what? Of attraction. Okay, but if it was the like poles, like your south and south or north and north, there will be a force of what? Of repulsion. Okay, explain your answer. Then we go on to say the unlike poles, they attract each other. So that means that the magnetic field lines causes a force of what? Of attraction. But the like poles causes a force of what? Of repulsion. 8.2.2, they're saying what will happen to the force if the distance between the poles is increased? Okay, so if we take both these magnets and we pull them, or we increase the distance between these two, okay, so what will happen is that now the force, okay, the magnetic field strength will start getting weaker and weaker as we move them far apart from each other. Okay, but as we move them closer or towards one another, the magnetic field strength then increases, because now the magnetic field lines are interacting. Magnetic field lines of one magnet is interacting with the magnetic field lines of the other magnet. Okay, so that is how simple it is to go on about answering these questions. You just apply what we talked about today, and voila, you are able to put or to understand your magnetic flux. You are able to understand your magnetic field. You are able to define what it is that we refer to as a magnet. What does a magnet have? What does a simple magnet has? And how can we see that this magnet is whole? Because it has to have a north as well as the south pole, even if it is the tiniest of the tiniest particle of the magnet. Okay, so I want to end this lesson today with a quote from Nelson Mandela, which says, "A winner is a dreamer who never gives up." Okay, so we're beginning this term on a high note, and I want you not to give up, because second term, even if you didn't do right with your first term, but second term, we are in it. Siyabangena, we're going to make this happen only by practice, only by following the properties of magnets and making sure that we study hard and present hard, give all our best on our schoolwork. All right, thank you for attending today's lesson. Join me next time, as we are still going to be doing magnets, but exploring the phenomenon that are related to the magnetic field and their importance as well. Thank you.